In considering complex differentiation, we came across the idea of analytic functions, which happen to be functions that are differentiable in the complex domain. So, so in this next sets of videos, I think three of them like that, we'll be looking at analytic functions, starting with holomorphic functions. Holomorphic functions. So by definition, a complex function f of z is said to be holomorphic on a domain D, which belongs to the complex plane, if it is complex differentiable at every point in that domain. So the complex derivative, of course, we have seen it a couple of times, is defined as f prime of z equals limit as h approaches 0 of f of z plus h minus f of z over h for h belonging to the complex plane. This limit must exist and be the same regardless of the direction from which h approaches 0 in the complex plane. In a previous video under complex differentiation, we already saw that the differentiability in the complex plane is not as straightforward as it is in the real domain because we have to consider differentiability along different paths because we have the real path x, we have the imaginary path y, and sometimes we may have to even consider when x is equal to y, when x is equal to y squared, or when y is equal to x squared, and things like that, depending on whatever function we are considering. So talking about real and imaginary components, like I just said, let z be equal to x plus iy. Then any complex function can then be written as f of z equals u of x comma y plus iv into x comma y, where u of x comma y is the real part and v of x comma y is the imaginary part. So to talk about all of these things, we need to look at the complex function f of z that is so defined. And of course, in the last video, we saw the Cauchy Riemann equations, which are very interesting. For f of z equals u of x comma y plus I v of x comma y to be holomorphic, for instance, the following must hold. Of course, just like we also talked about differentiability in the complex plane, right? Differentiability doesn't just stop at being able to differentiate across the paths, but you must also be able to see that differentiability depends on the system obeying the Cauchy Riemann equations, which are defined as partial u partial x equals partial v partial y, of course based on this u and v here, and then partial u partial y equals minus u partial v partial x. And these are called the Cauchy Riemann equations. And the last video was totally dedicated to that. In case you need to know how we derived this, you want to check out that video. So, of course, this example has been following us everywhere. F of z equals z squared. And so what we can do here is we can expand. Step one, expand. Z squared is x plus iy squared. And when you expand that, that's uh, x squared plus 2i xy plus I squared y squared. And by the time you simplify all that, you get x squared minus y squared plus I2xy. Of course, it was plus I squared y squared, but I squared is minus 1. So that's why this one becomes minus. So you have x squared minus y squared plus I2xy. So the real part is u equals x squared minus y squared, the one without I. And the one with I is v, which is 2xy. So the next thing you want to do is to compute partial derivatives, and u sub x, which is partial u partial x, is 2x, u sub y is minus 2y, v sub x, that's partial v partial x, is 2y, v sub y is 2x, that's partial v partial y, is 2x. And of course the rule says for Cauchy Riemann, to now check Cauchy Riemann, u sub v equals v sub y, u sub v is 2x, v sub y is 2x. That holds. Then on the other hand, u sub y is minus 2y, v sub x is equal to 2y. And we know that u sub y should be minus v sub x, and that means minus 2y is minus 2y. So in that, if since all the conditions are met, therefore f of z is z squared is holomorphic everywhere. Okay, so it means that we can say that every complex function that obeys the Cauchy-Riemann equations is holomorphic. That means it is differentiable at every point in the given domain D that is in the complex plane. And of course, we have this notorious example, f of z equals z bar, that's the conjugate of z, and the conjugate z is x plus iy, so the conjugate of z is x minus iy. So the real part is x and the complex part is minus y, as you can see here. So if you compute the derivatives, u sub x, that's partial u partial x is 1. Partial u partial y is 0 because there's no y here in the first place. Then partial v partial x is 0 because there's no x here. And then partial v partial y is minus 1. So now partial u partial x should be equal to partial v partial y for Cauchy Riemann equations to hold. So, but because u sub x is not equal to v sub y, thus we can say the function, that is the conjugate function, is not holomorphic everywhere. All right. So, um, maybe it's holomorphic in at some point, right? Of course, it's holomorphic because we can get results for everything, but then the fact that they are not, it doesn't obey the Cauchy-Riemann, then it's not holomorphic everywhere. Then we talk about infinite differentiability. So a key theorem we see here is that if a function is holomorphic, that is, it is differentiable, it is holomorphic everywhere, right? If a function is holomorphic, then it is infinitely differentiable, all right? So if a function is holomorphic, then it is infinitely differentiable. That is, you can find all the possible derivatives. So you can find the first derivative, second derivative, up to the nth derivative, and that exists for all n belonging to the natural real numbers. That's 1, 2, 3, and so on. So additionally, the function can be written as a power series, which is f of z equals summation from n equals 0 to infinity of an into z minus z naught raised to power n. Don't mind me, I keep saying z, z, and all that. Just take it like that. It's a mixture of British and American English together. All right, so now we are coming to the idea of series now, and we are going to see. So down the line, we're going to talk about series, in the context of complex numbers like that. So let's talk about power series expansion then. So if you consider f of z equals 1 over 1 minus z for absolute value of z less than 1, I mean, for this to hold, right, it means that um z must lie between minus 1 and 1. That's what this means. So that's what we have right here. So this can be expanded as f of z equals 1 plus z squared plus z cubed plus all of that. And this shows that the function is analytic and infinitely differentiable. So you can express this function, which looks like a rational function, into a polynomial. I know polynomials are differentiable everywhere. And of course, how do we move from here to here? You may be wondering, that's one relationship between a rational function and geometric function, right? If you talk about things like sum to infinity, you have 1 over 1 minus z. That's what is it 1 minus z or z minus 1 now? It's easy to flip things over like that. Yeah, 1 minus z, that's cool. So, all right, so we have this. So, of course, f of z is 1 minus z raised by minus 1. And then we can use the general rule of the general expansion, right? So here we just say, okay, before I even start that, you can recall, in case you've done this before, and if you've not done it, just take note that if you have a plus b raised to power n, you can expand it as a raised to power n, b raised to power 0, all over 0 factorial, plus n, the power comes down now, a raised to power n minus 1, b raised to power 1 over 1 factorial, and it goes on like that. Next, you have n into n minus 1 into a raised to power n minus 2, b raised to power 2 over 2 factorial, and the next term there will be n into n minus 1 into n minus 2, all right? A raised to power n minus 3, b raised to power 3 over 3 factorial, and that goes on like that, okay? So if we do the same for the expression there, right? If we have f of z equals 1 minus z raised to power minus 1. So that means you can have that expanded as first 1 raised to power minus 1, which is the biggest power, then minus z raised to power 0, all over 0 factorial, plus minus 1 comes down, and you have 1 raised to power minus 1, 1 raised to power minus 1, that's minus 2, then minus z raised to power 1. So at any point in time, if you add the powers, it should give you minus 1. Minus 1 plus 0 is minus 1. Minus 2 plus 1 is minus 1. So now this is over 1 factorial. Then I go again. I have minus 1, minus 2, 1 raised to power minus 3. That's minus 2 minus 1. Then minus z raised to power 2, all over 2 factorial. Okay, I'll do one more. So we have minus 1, minus 2, minus 3, 1 raised to power minus 4, then minus z raised to power 3, minus z raised to power 3. So minus z raised to power 3 all over 3 factorial. And that goes on like that. So if you tidy all of this up, you see what you get. Of course, all the 1 raised power minus 1 is like 1 raised power minus 1 is 1 over 1 raised power 1, which is 1. So all of that is going to be 1. So you can already know that everything, all this is 1. All this is 1. So you don't get confused with that. And then we know minus z raised power 0 is anything raised power 0 is 1. 0 factorial is also 1 plus. Okay, here now we have, okay, minus 1. Okay, I can still tidy up a bit. Minus 1 minus z all over 1 factorial is 1 plus, so I can do this minus 1 times minus 2 into z squared, because if you square this, you get z squared. Or 2 factorial is 2 plus minus 1 minus 2 minus 3, all right, minus z raised power 3. If you expand that, and you get 3 factorial, that's 3 factorial is 3 times 2 times 1, and all of that go. So this cancel all of that. And then we have f of z now to be equal to 1 over 1 is 1. Then minus and minus is plus, so you have plus z. And then here, these two cancel this. To minus and minus is also plus. You have z squared. And then coming here, you have minus and minus and minus. 4 minus is that's still plus z raised by 3. So now you see, so you now see why, uh, so you see why f of z is equal to 1 over 1 minus z is the same thing as 1 plus z squared plus z cubed, and so on and so forth. Interestingly, what if you want to translate this back to where you came from? Okay, you have 1 plus z squared plus z cubed, and so on and so forth. So, this is a geometric progression, right? This this is a GP. This is a geometric progression. This is a geometric progression. All right. It's a geometric progression with first term, first term equals 1. If you like, you can call it first term A equals 1. Then common ratio. That's one thing for geometric progression. Common ratio would be common ratio R, right? Common ratio R, which is equal to R, is equal to Z over 1 or Z squared over Z. And all of that is Z. So the sum to infinity, right? Uh, the sum to infinity, the sum to infinity is given as S infinity, which is equal to A over 1 minus R. And what is A? A is 1, okay? First term, then 1 minus z. So you see now, we have a cycle. So the geometric progression can be turned to this expression, and this expression can be turned back to that, like I did by expanding there. So we see that that is actually true. But in the context of complex numbers now, the fact that you can translate f of z equals 1 over 1 minus z into f of z equals 1 plus z squared plus z cubed tells us that the function is analytic and infinitely differentiable. Okay, so for Python visualization, right? You know, if we expand this, we know the u component is x squared minus y squared, and the v component is 2xy. And if we, I think I showed this in the last video too, showing that they are actually orthogonal, that u and x intersect continuously at an angle 90 degrees, as you can see in all of these places. So this is for the real part. This is the imaginary part now. So, and then when they also intersect, they intersect at 90 degrees. So we have numerical verification of Cauchy Riemann equations. So imagine if you define u in terms of x and y, and we want to return x squared minus y squared, and we define v in terms of x and y, and we want to return 2xy. So taking a very tiny h, and we do the derivatives, right? So we can have u of x, and we define u of x plus h comma y, and do all of that. By the time we run all this, we see u of x is 2.0 something something, v of y is 2.00 something something, roughly 2 in each case. Then u of y is minus 2.0 something something, minus vx is minus this. So that establishes the fact that partial u partial x is equal to partial v partial y, and that partial u partial y should be equal to minus partial v partial x, and that is established. So let's talk about the harmonic property So for the harmonic property, right, if f of z is holomorphic, then u and v satisfy Laplace's equation, which is uxx plus uyy equals 0, and uxx plus vyy equals 0. So example, if you have for u equals x squared minus y squared, right? So uxx is 2, uyy is minus 2, so that uxx plus uyy is equal to 0. Thus, you can say u is harmonic, right? U is harmonic in that sense. And, how do we actually pull this off, right? Let's see if you have, so for the harmonic property, how do we derive the harmonic functions? I want to try to do that. So from Cauchy Riemann equations, we know that ux is equal to vy, and of course, um, v, and of course, uy is equal to minus vx. So let's see what happens here. So in this case now, if we try to differentiate with respect to x here, this will be uxx, and that will be equal to vyx. And here we have, if we differentiate this one with respect to y now, we have uyy equals minus vxy. Okay. So if we then adding both, what do we get? If we add both, we get uxx plus uyy. This uxx plus this uyy now is equal to vyx minus vxy. Interestingly, uh, eh, generally speaking, anytime, any day, um, you should know that vyx is always equal to vxy. It's anyhow you start. You can check with any function at all. So in that case, we have uxx plus. So in that case, you then have uxx plus uyy equals vyx minus vyx, making this side 0. So you have uxx plus uyy equals 0. You can do the same. You can do it you can flip it over too. Okay. Um, so that establishes the harmonic property. So we're able to derive this too. So well, we have this example already done. In summary here, we see that a function is holomorphic if the complex derivative exists, number one. Number two, Cauchy-Riemann equations hold, and partial derivatives are also continuous. So the key properties are that they are infinitely differentiable, equal to its power series, and real and imaginary parts are both harmonic like that. So, and we have some practice problems. And as usual, I like to solve two of them. You have questions 1 to 10, you have questions 11 to 20. So for question 1 to 10, I'll take number 2. So number 2, we want to determine whether f of z is equal to z bar squared is holomorphic. And then we answer question 18, which want to determine whether f of z equals z over absolute value of z is holomorphic. So let's go on and do that. Okay. So question 2 now, to determine, that's problem 2, to determine whether f of z equals z bar squared, the square of the conjugate of z is holomorphic. Holomorphic. Okay, so step one, we write in terms of x and y, write in terms of x and y. So in that case, then we have that, of course, we know z is x plus iy, and that implies that z bar is x minus iy. So if that is the case, that means f of z being z bar all squared is actually the same thing as x minus iy all squared. So if we tidy that up, it means that f of z is equal to x squared minus 2xyi, this I here, then plus I squared y squared, like that. So that means f of z is equal to x squared minus I 2xy minus y squared, like this, because I squared is minus 1. So then that means f of z is equal to x squared minus y squared minus I 2xy. So what does that tell us? It means that u of x comma y, the real part is x squared minus y squared. On the other hand, v of x comma y is equal to minus 2xy, this one. So with all of that in place, we can go for step two. Step two, we compute partial derivatives. Compute partial derivatives. Compute partial derivatives. So that means that, so here we have u sub x, differentiate u with respect to x, that's 2x. Then you get u sub y, that is minus 2. This is 2x, this is minus 2y. Then on the other side, you have v sub x, that is minus 2y, and you have v sub y, that is minus 2x, like that. So, so u sub x is 2x, u sub y is minus 2y, v sub x is minus 2y, v sub y is also is minus 2x. So in step three now, step three, we check. Step three, check the Cauchy Riemann equations, the Cauchy Riemann equations. Check the Cauchy Riemann equations. So we check ux equals vy. Is that true? Ux is 2x, vy is minus 2x. That doesn't hold. So that is not equal to, okay, maybe I do it this way. Ux is 2x and vy is minus 2x. So not correct, not equal. On the other hand, we have on the other hand, uy should be equal to minus vx, right? So here, what is ui? Ui is minus 2y, and vx is also minus 2y. Vx is also minus 2y. This is correct, but as far as one breaks down, then it's everything breaks down totally. So in this case now, it simply means that we can't work with this. So now for both to hold, now it means that x and y have got to be 0. So that's the only thing. But apart from at 0, that it doesn't work at any other point again. So we have vy equals vy equals ux and ui equals minus vx. So that one is okay. So, while this holds, right, the only condition for this to hold is if, say, if we have vy equals minus vy, now we see if vy is minus ux in this case. So that means we have minus 2y, and that is equal to minus 2x minus 2y, which is equal to 2y. So, and that only implies that, so that implies that 2y can only be 2y implies, so all this basically imply that y can, this only can hold at y equals 0. So in conclusion, we can say that both equations hold, both equations, this is ux uy minus vx. So okay, uy is minus 2y, right? Minus vx. Minus Vx should be 2y. Yeah, I think that was one thing there. So if you look at both, if you then look at both, it means that they can only hold at y equals 0. At both x and y equals 0. So this only holds this minus 2y, this is minus 2y, which is not equal to 2y actually. So only holds holds for x equals 0. This one too only holds for y equals 0. So the conclusion is that both equations only hold only at x comma y equals 0, 0. Therefore, f is not holomorphic everywhere. F is not holomorphic everywhere. It's not holomorphic everywhere. Then 2, it is differentiable. It is differentiable. It is differentiable only at z equals 0. Okay, we have that there. So don't forget these two. One is 2x is equal to minus 2x, and then minus 2y is equal to 2y. And this can only hold when x is 0 and y is 0. And that is why this is only holomorphic at 0, 0. So it is not holomorphic everywhere. So let's move on to problem 18. Problem 18. So for problem 18 now, I want to determine whether f of z equals z over absolute value of z is holomorphic. Holomorphic. Okay. So what do we do? Step one. Okay. Step one here. Step one. So the first step here is we can write this in polar form. Right. So polar form makes things easy when they look complicated like this. Write in polar form. So if you write in polar form, that means you're letting z be r e raised power I theta for absolute value of z equals r, right? That's established. Then it means that f of z equals z over absolute value of z is actually equal to r e raised power I theta all over r is simply the same thing as e raised power I theta. So you see, this makes it pretty simple, and then you can move on to other things. So step two now, in step two, you can express in terms of x comma y. Okay, so e raised power I theta now can still be expressed in terms of x comma y, because of course we know that cos theta, e raised power I theta is cos theta plus I sine theta. And we know already that cos theta is x over r. And we know r is absolute value of z. So this is x over modulus r, which is square root of uh, uh, cos theta is x over r, yes, which is x over r, which is x over square root of x squared plus y squared. In case you're wondering, right, it's from this idea that if you have a complex number, this is angle theta, so this is y, this is x, so and this is r. Okay, so cos is opposite over hypotenuse, x over r, and for my Pythagoras theorem, r is square root of y squared plus x squared, because r squared is x squared plus y squared. That's where we are getting all this from. So it's established now that cos theta is equal to x over square root of x squared plus y squared. This, on the other hand, we have sine theta. So we have sine theta, which is opposite. Sine theta is opposite y all over hypotenuse r. That is y over square root of x squared plus y squared. Okay, so sine theta again is y over square root of x squared plus y squared. So we have this established also. Then we move on to the next thing. So with all this in place now, that tells us we know what we are looking at is e raised power I theta. So e raised power I theta, which is equal to cos theta plus I sine theta, can simply be written as e raised to power I theta is equal to cos theta, that is x all over square root of x squared plus y squared, plus I sin theta, that's y all over square root of x squared plus y squared. So uh, in terms of complex functions, right, we can then say u of x comma y, the real part is x all over square root of x squared plus y squared, while v of x comma y is equal to y all over square root of x squared plus y squared. So, and with that in place, then we can then go ahead and analyze differentiability. So that's step 3 now. Step 3, analyze differentiability. Analyze differentiability. So first of all, you know that this when x is 0 and y is 0, the two functions will not be defined. So that's settled, right? So first of all, the function is not defined. It's not defined at 0, comma 0. When x is 0 and y is 0, these two functions will be undefined. First thing. Secondly, near 0, comma 0, the direction, the direction the direction theta, that's the argument theta, changes discontinuously. So it changes discontinuously. So if you try to visualize all that, it changes discontinuously. Then apart from that, um, partial derivatives, partial derivatives involve square root of x squared plus y squared. So if you take partial derivatives of both parts, we always have square root of x squared plus y squared, you know, in denominator, in denominator. So that shows singular behavior. That implies singular behavior. So that means that, so for some values of x and y, we can get I mean, that shows singular behavior because when x and y are 0, right, the functions will be undefined. So that's some initial analysis there. Then in step 4 now, we can then have a conceptual argument instead of actually doing it, differentiating straight up. So we can have a conceptual argument as follows: that the function depends, the function depends only on the angle theta, only on the angle theta, not smoothly on x comma y. And one thing we said the other time is, for you to know that a limit exists, right, the limit must only depend on r in polar form. If it depends on theta, then it's not, the limit doesn't exist in that case, and that's what we have playing out here. So the function depends only on the angle theta, not smoothly on x comma y. So in that case, approaching approaching the same point approaching the same point from different directions gives different values, will give different gives different values. So what do we say? Thus the limit defining the derivative, which is limit as h goes to 0 for f of z plus h minus f of z all over h, depends on direction. So it depends on direction. So it doesn't give the same result everywhere. So what do we conclude then? So based on that, we conclude that f of z equals z over absolute value of z is not holomorphic. It is not holomorphic anywhere because it totally depends on the angle. It's not holomorphic anywhere. The other example we did actually is holomorphic at 0, comma 0. But this one is not holomorphic anywhere. Then it it is not, it is not even continuous. It is not even continuous at z equals 0. Z equals 0 implies that x comma y is equal to 0, 0. So at 0, 0, it doesn't even, it's not even continuous. Then finally, it fails, it fails complex differentiability. It fails complex differentiability, differentiability everywhere. Okay? Feels complex differentiability everywhere. And that's about question 18. So again, look at the questions 1 to 10. Try your hands. I've done 2, then I've done 18. Try your hands on them. Let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed to this channel already, I must thank you very much for doing that. If you have not subscribed, why not go ahead and subscribe right away? And then, of course, after subscribing, you can hit the notification bell so that you can always get alerted each time a new video is released. Then, of course, having done that, you can become a member of the channel by clicking on join. That gives you special privileges like get to see some videos first before other people. And apart from that, you can also see some videos exclusively as a member of the channel. You could also request for PDF copies of my notes, and then we can hang out together physically if you're in the same geographical location at any point in time, or we can also hang out online to discuss whatever interests you on my channel, be it mathematics, data analysis, data science, machine learning, writing books, making YouTube videos, teaching maths on YouTube, anything at all that interests you, we can discuss all of that as a member of the channel. Ultimately, don't forget to comment, like, share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.